Lesson 8 is transformations and congruence. So 8.1 talks about general congruence, like with any shapes, and then 8.2 focuses more on congruence of triangles. So two objects are congruent if they have the same shape and same size. So a lot of times we maybe mix up congruent with equal. There are some slight differences that we'll get into today, but congruent basically means the same exact size, same everything, I guess, just different object basically. So basically like two twin objects, I guess. So if corresponding angles of the figures have the same measures, they have the same shape. So you can kind of see like these all have the same angle measurements between these two figures, all their corresponding angles are the same. You can see that they also have the same shape. So those two go hand in hand. And then if the corresponding sides have the same length, then the figures have the same exact size. So you can have situations where all the angle measures are the same, but maybe one object is double the other object. So as long as all the side lengths are the same, then they are congruent, then they're the same exact size altogether, size and shape. Okay, so before we get into these tables down below, you probably have seen like the symbols that we use to show that like segments are the same length or angles are the same size. So you can see like between A and D, there's that one tick mark right here, and between K and N, there's that one tick mark right here. That just means that those are the same size. And then similarly, any side that has like these both have two tick marks and saying that those are the same length, these have three, those are the same length, and so on. And then it works the same for angles. So since this angle only has one line and this angle has one line, those are the same exact angle measurement. This one has two, this one has two, those will be the same angle measurement, and so on. So there's lots of little like shortcuts that we can use in math to show that something has the same measurement. Okay, so moving down to these two tables below, on the left you can see there's the equality statements, and then on the right there's the congruent statements, and they look very similar. We just can use these to decipher the difference between equal and congruent. So I'm not going to go through every single line because they are all just kind of like copycats of each other, but I'll go through a couple lines of each. So under equal angle measures, this is read as the measure of angle A equals the measure of angle K. So the measure of angle A equals the measure of angle K. We already kind of talked about that. It shows it on the graph by the fact that these both have the one angle line. But if we're just talking about congruence as opposed to equality, we don't actually have to put the measure symbol in front of it. So we can just write it as the angle A is congruent to angle K. So notice like there's a couple little differences between these, and it's just one of those like small specific geometry things that we have to get comfortable with. So here we have an equal sign, and we can't just say angle A is equal to angle K because they're not the same angle. In order for them to be equal, they would have to be the exact same angle, like same location and everything. So that's why when we're using equal sign, we have to put that M in front of it. So we can say the measure of angle A is equal to the measure of angle K. Like say angle A is, I don't know, 110 degrees. We can say that's equal to the measure of angle K, which is also 110 degrees. Versus this little equal sign that has the squiggly line over it, that means congruent. So we can say angle A is congruent to angle K because if they're congruent, they just need to have the same measurement. They don't need to be in the same location. They are not the same exact angle. They just have the same size. And then similarly for the segments. So over here, this says, since there's no line on top of the like AB, that's saying the distance between A and B. So the distance between A and B is equal to the distance between K and L. So when you just have the two letters together, it's not saying segment AB, segment KL, it's saying the distance between points A and point B equals the distance between point K and point L. And we could also see that on our picture by these two little tick marks. So we can say that their distances are equal to each other. And then for the congruent statement over here, this line above does say segment AB. So segment AB is congruent because it has a little squiggly over the equal sign, for lack of a better term, is congruent to segment KL. So when it's congruent, we can say the two segments are congruent. When they're equal, we can't say two segments are equal unless they're the exact same segment, like segment AB equals segment AB, where they're in the same exact location. So I know it doesn't feel like a huge difference, but it's just one of those like kind of minor but also important aspects about geometry. So I would just go ahead and maybe like write this table down, store it away, keep it, especially for when we're writing proofs and stuff like that, or just take a picture of it, save it to your favorite so you can go back and reference it. Okay, and then moving down here. So equal, I know I've kind of said it, but equal just means everything is exactly the same. So it is the same size and it is in the same exact location. So we can't really say that like two different segments are equal. We couldn't say AB equals KL. We could say their measurements were equal, but we can't say that they are equal because they're not in the same exact spot. Whereas congruent means same shape, same size, measurement, but different objects, different locations. So we can say that segment AB is congruent to segment KL. They're the same exact size. They're just in a different spot. They're on a different object altogether, but they're the same everything else. They're just on a different object, I guess. Okay, and then down here before we move on, so quadrilateral ABCD and quadrilateral KLMN are the same shape because all their corresponding angles are equal. So those are like the little angle measurements that we compared, like angle A and angle K. And then they're the same size because all their corresponding side lengths are equal. So like how AD and KN had just the one tick mark, those are corresponding. They're the same length, they're equal. So therefore, we can conclude that quadrilateral ABCD is congruent to quadrilateral KLMN. Okay, so we can't say they're equal because they're not the same thing. They're two different objects, but we can say that they're congruent. So moving down to the next section, this is still in 8.1, which is the very end of it. So if a set of rigid transformations can superimpose one figure onto the other and they coincide, then they must be congruent. So a couple like weird, funky words there. So superimpose just means like if I can use transformations to make one object land on the other, that's superimpose. And then and they coincide is like all the points line up perfectly. So basically, if I were to reread this with my like interpretation, I guess, if a set of rigid transformations can make one object fall on another and their points line up exactly, then they must be congruent. So we're going to take the blue triangle ABC, and we're going to transform it and see if it coincides with EFG. Okay, so fortunately we already have the transformation. We don't have to figure out which one it is exactly. We're going to rotate it 180 degrees. The mapping statement for rotating something 180 degrees is xy maps to negative x, negative y. So that just basically means that we take our original points and their signs become the opposite. So if I apply that transformation to point A, I'm going to call this A prime. That's going to change the signs of my points. So it doesn't like make them negative, it makes them the opposite of what they originally were. That's what these minuses do. So instead of -4, it's going to become a +4, and then instead of -4 right here, it's going to become a +4 right here. And then because it's just mapping to negative x, negative y, we don't have to switch the order or anything like that. I feel like when we switch the order, that's when things get a little weird. Okay, so for B, if we rotate it 180 degrees, then B prime is going to be, instead of -1, +1, and then instead of -3, it'll be +3. And then for, and then for C, if I go ahead and rotate C 180 degrees, then C prime is going to be, instead of -2, it'll be +2, and then instead of -1, it'll be +1. So let's just see how those points line up with the new figure. So I'm just going to go ahead and label A, B, and C prime on the graph. So A prime is going to be 4, 4. We already have a point there, so this is A prime. B prime is 1, 3. We already have a point there, so this is B prime. And then C prime is going to be 2, 1. We have a point there at C prime. And then if you look, we have obviously points on all three same places. Ignore how that line is a little bit off. I just didn't connect it properly. But what we did is we used a set of rigid transformations. We rotated 180 degrees to superimpose one figure onto the other to make it line up with it, or make it like land on top of it. And by doing that, they coincided, meaning the points lined up perfectly. So they are congruent. So we can say the little like math shorthand for therefore is 3 dots like that. So this is therefore. We can say triangle A, B, C is congruent to triangle E, F, G. And then before we move on, there is one important thing to note when you're writing the congruent statement. So we said, therefore, triangle ABC is congruent to triangle EFG. It's important that you match up the vertices, like the proper vertices, so that they are in the correct order. So what I mean by that is, like, when we took A and we rotated 180 degrees to A prime, that was E. So in the first spot was A, and the first spot with our second triangle should be E. So this is the first spot, this is the first spot. And then for like B, when we rotated that 180 degrees, B prime landed with F. So this would have to be, B is in our second spot, so F would have to be in our second spot. And then the last one for C, when I rotated that 180, it landed, C prime landed in the same spot as G. So since C is in the third spot, that G would have to go in the third spot also. It just has to fall in the same order as like the corresponding angle that it goes with. So last little thing in other terms, I could not have said like triangle ABC is congruent to, say, GEF, because it doesn't match up the corresponding angles, so you just have to be careful with that. Okay, so 8.2, we're going to talk a little bit about the graphic, and then we're actually going to do something that is more like interactive in the workbook. So 8.2, congruent triangles. So this is just comparing different like congruent statements. So we can say triangle ABC is congruent to triangle EEF, just based on the fact that their corresponding side lengths are the same length and their corresponding angles are the same measurement. And just kind of going back to what I said at the end of 8.1 about the order, notice that the corresponding angles are in the same order here, right? So they have angle A that's corresponding with angle E, because those have the same measurement, because they just have one angle measure, and A and E start off the way that we title our triangles. And then for B and F are corresponding because those have the same angle measurements. Those both come second. And then for angle angle C and angle G, those are corresponding because those both have the same measurement, and those both come third. So you just have to be super careful with the order to make sure that you're lining up the corresponding angles properly or in the correct order. And the second part just goes more into that. So I'm not going to talk too much about this. You guys can look at the graphic. You can read that like angle A, not highlighting, sorry, angle A is congruent to angle E. Side length or segment AB is congruent to EF. Just all that information shows us that because they're all congruent, because all the corresponding sides are congruent, all the corresponding angles are congruent, we can declare that the two triangles are congruent. What I mostly want to focus on for 8.2 is using the congruent angles activity in your 8.1 workbook to decide if those angles, or sorry, if those triangles are congruent. And I'm just going to screen share and snip that to this video. You're welcome though to like kind of split screen and do it on your own while watching this video as well. 8.2 talks about congruent triangles, and we already talked about this first graphic right here, talking about how corresponding angles are congruent, the corresponding sides are congruent, so we can state that the two triangles are congruent as well. Basically, in order to prove that two triangles are congruent, we can, or we should be able to apply a set of rigid transformations and have those two triangles coincide with one another. So basically, we want to get the two triangles to line up perfectly, and that's what allows us to prove that they are congruent. So this next section, they're going to take you step by step with a few different rigid transformations, which remember that rigid transformations are translations, reflections, or orientations. I'm not going to read through this. I think you guys can read through it on your own. The main thing I wanted to focus on from this page was this activity down here, which is basically going to allow us to do what they just kind of did in the notes. So congruent triangles, our goal is to apply some rigid transformations and get the two triangles to line up. So in math terms, we want to superimpose one triangle onto the other and get them to coincide. Like I said, put one triangle on top of the other and get the points to line up exactly. So our goal is to get triangle ABC to line up with A prime, B prime, C prime. So to get the green triangle to line up perfectly with the red triangle using only rigid transformations. So the first thing that I notice is the orientation of the two triangles is different, meaning that they're kind of like pointing in different directions or facing different directions. And I noticed that sometimes the mouse is not showing up in the recording, so I'll do my best to like explain what I'm clicking on in case that's the case here as well. So because the two triangles do not have the same orientation, that means that we either need to apply, or we will have to apply at least a rotation or a reflection, because those are the two rigid transformations that would change the orientation. A translation would not, because that's just moving it left, right, up, or down, but not spinning it around or reflecting it. So I think the first thing I want to do, and what's so nice about this activity, which is why I want you guys to play around with it on your own as well, it's so quick and easy to apply like different transformations. I just need to click on the different degrees for the measurements. I can switch between clockwise and counterclockwise. I can apply a reflection really easily. So it's just kind of nice to be able to play around with it and actually experiment with it for yourself. So I'm going to reset this. I'm going to try, the first thing I want to try is a 180 degree rotation. And if I'm going 180 degrees, it doesn't matter if I go clockwise or counterclockwise. I'm going to go ahead and apply it. Okay, so that didn't really work. So it's not the right rotation, which this is my first time doing this one also. So we're doing it for the first time together. So that's why it's so nice. Like I didn't have to like get out a piece of paper and graph it. I'm able to just click the button and see that it didn't work. So I'm going to try something different. I'm going to try a reflection over the y-axis. And okay, maybe that looks a little bit better. So I'm going to try that. So you have to make sure that you click apply to make it stick there. And then now I'm going to try a rotation. So I want to go clockwise. So I need to click over on the clockwise arrow, and then I'm going to try 90 degrees. So we're getting closer. It's like really close now. So it's at least the right orientation. To make that triangle stick there, I need to click on apply rotation to put my new triangle there. And then now it looks like I just have some sort of translation. It looks like I just need to slide it a little bit to the left. So we'll go down to these two sliders where it says H equals and K equals, and those will be our translations. So in general, we use H as a horizontal translation. So if I move the H slider, you'll see that the triangle will move right or left depending on what I make H equal to. And then for K, we use K to represent vertical translations. So you'll see that if I drag the K slider, it moves it up or down depending on what I make K equal to. So I just need to move my purple triangle a little bit left, it looks like, to make it line up with the red one. So I'm going to go to the H slider because that's left or right. And I'm going to go in the negative direction. So I'm going to make H -1, and then it'll line up perfectly. And then it kind of gives you that like Hey, good job, you did it. Because we did make this green triangle ABC coincide perfectly with A prime, B prime, C prime, and that proves that they are congruent. It proves that they have all the same angle measurements and all the same side lengths. So I would go into workbook 8.1, and you can do as many of these as you want. You could just click new and see how many you can get to line up just using only rigid transformations. Like I said, it's kind of nice that you don't have to like sit there with a piece of paper and graph each individual one. You just get to click around with the different transformations until you can get them to line up.